Perhaps the greatest achievement of late 20th and early 21st century astrophysics is the arrival of a consensus model of the entire universe, lambda CDM cosmology. For countless generations, humans have marveled at questions such as, what is the universe? What makes it up? How far does it go? How did it come into existence, and how long ago? How did it grow to be the way it is today, and what will its ultimate fate be? Today, after unprecedented measurements of galaxies throughout cosmic history, all-sky imaging of the universe at microwave wavelengths, and thousands of supernovae and other transient events across the universe, we finally have answers to these questions. Our universe, made of 68% dark energy, 27% dark matter, and just 5% normal stuff, began from a small, dense, nearly perfectly uniform state some 13.8 billion years ago in a hot Big Bang. It has been expanding, cooling, and gravitating ever since. At least, that's the consensus picture. But now, the James Webb Space Telescope, with its unprecedented infrared eye, is rewriting what we thought we knew about the early universe. Instead of showing the formation of just a few small stars, which would satisfy the timeline of the hierarchical structure formation theory, the telescope is now sending back data that poses serious difficulties for the modern creation myth. As it looked deeper into space, the telescope revealed anomalies that challenged long-held prejudices about the origin and development of the universe and shed a brilliant light on profound scientific and philosophical questions. Indeed, the galaxies captured by James Webb existed far earlier than anyone had expected them to. In other words, somehow, the universe is building galaxies earlier and faster than our theories predict. And this was no minor discrepancy. The finding is akin to parents and their children appearing in a story when the grandparents are still children themselves. Another way to imagine it is like going to a nursery to visit your newborn and finding a room full of teenagers, which is really disturbing, to say the least. So, what does this mean for the history of the universe? Frankly, Webb's discovery could have significant implications for cosmology, as it implies that current theories about the formation and evolution of galaxies could be incorrect or incomplete. To explain the existence of these galaxies, scientists may have to revise models of the universe's evolution and galaxy formation processes. One possibility is that these massive galaxies formed differently from the galaxies closer to us. For example, there may have been an unknown mechanism until now that allowed the formation of massive galaxies in a short period of time. Another possibility is that these galaxies are the result of exceptionally rapid mergers between smaller galaxies in the early universe, which would also require a revision of current models. In any case, the discovery made by the James Webb Space Telescope represents a significant advancement in the study of cosmic evolution and galaxy formation. This finding is likely to prompt astronomers to develop new theoretical models and seek more observational evidence to better understand the history of the universe and the properties of these enigmatic distant galaxies. But note that the impossibly massive galaxies were not an isolated incident. Astronomers have long thought that newly minted galaxies that began merging together just after the Big Bang, about 13.7 billion years ago, were too fragile to form any noticeable structures like spiral arms, bars, or rings. Those galactic features were thought to form during a time at least 6 billion years after the Big Bang. However, according to another remarkable study made by James Webb, these delicate shapes could have manifested as early as 3.7 billion years after the Big Bang, which is almost at the beginning of the universe. As Christopher Consolis, an astronomy professor at the University of Manchester in the UK and a co-author of the new study, said in a statement, based on our results, astronomers must rethink our understanding of the formation of the first galaxies and how galaxy evolution occurred over the past 10 billion years. These findings come on the heels of another announcement presented by a different group of researchers, also based on Webb's data, which showed these early galaxies produced far fewer heavy elements than previously expected. However, the relationship between a galaxy's chemical composition and its evolution into a well-defined structure is not very well understood. Much of scientists' previous understanding of galaxy evolution came from data gathered by the Hubble Space Telescope, which is legendary in its own right but still has only so much resolution. While Hubble's data showed early galaxies had irregular shapes, as was expected during galaxy mergers, Higher resolution data from James Webb is peering deeper into the universe to reveal that those early galaxies actually had well-defined structures like our own Milky Way. The new findings were based on an analysis of 36 galaxies, which astronomers say is the biggest sample that has been studied thus far with Webb's data. In the words of Leonardo Ferreira, an astrophysicist at the University of Victoria in Canada and the lead author of the new study, for over 30 years, it was thought that these disk galaxies were rare in the early universe due to the common violent encounters that galaxies undergo. The fact that James Webb finds so many is another sign of the power of this instrument, and that the structures of galaxies formed really early in the universe, much earlier in fact than anyone had anticipated. According to the new study, the team classified the sample set of close to 4,000 galaxies from the early universe by shape, disks, point sources, and spheroids. Team members further classified them as smooth or structured, with galaxies in the latter group featuring bursts of star formation and indications of mergers with other galaxies. Results showed that relatively well-defined structures in the universe formed a lot quicker than previously thought, following what is known as the Hubble sequence, which is the standard classification of galaxies by their visual properties as ellipticals, lenticulars, and spirals. The latest findings suggest a need for new ideas that explain how galaxies evolved over the past 10 billion years. Elsewhere, there have been other Webb observations in which the evidence behind science's basic understanding of the universe has been found to be alarmingly inconsistent. Take the matter of how fast the universe is expanding. This is a foundational fact in cosmological science, the so-called Hubble constant. Yet, scientists have not been able to settle on a number. There are two main ways to calculate it. One involves measurements of the early universe, such as the sort that Webb is providing, and the other involves measurements of nearby stars in the modern universe. Despite decades of effort, these two methods continue to yield different answers. At first, scientists expected this discrepancy to resolve as the data got better, but the problem has stubbornly persisted even as the data have gotten far more precise. And now, new data from Webb have exacerbated the problem. This trend suggests a flaw in the model, not in the data.
So, is it time to dethrone the Big Bang Theory? Maybe. As Dr. Luke Barnes, a postdoctoral researcher at Western Sydney University, said, it's more likely that the story of the Big Bang will become part of a larger story. After all, Nicholas Copernicus's model of a sun-centered universe was never overthrown per se, but Johannes Kepler simply refined the orbits of the planets. Isaac Newton explained the forces, and modern astronomy has placed our solar system and our galaxy in expanding space. We can only use observations and theory to peer so far back in time. So, for the Big Bang, there is plenty of room for a prequel that explains what happened in the earliest fraction of a second of the life of the universe. Similarly, we can only see so far in space to our cosmic horizon. The universe beyond the horizon could have the same properties as ours, or we could be part of a vast and variegated multiverse. But as in the past, if you want to start a cosmic revolution, you've got to do it right. We all know that there are some problems with the Big Bang Theory. Since scientists first proposed the Big Bang Theory, many people have questioned and criticized the model. Here's a rundown on some of the most common criticisms of the Big Bang Theory. First, it violates the first law of thermodynamics, which says you can't create or destroy matter or energy. Critics claim that the Big Bang Theory suggests the universe began out of nothing. Proponents of the Big Bang Theory say that such criticism is unwarranted for two reasons. The first is that the Big Bang doesn't address the creation of the universe, but rather the evolution of it. The other reason is that since the laws of science break down as you approach the creation of the universe, there's no reason to believe the first law of thermodynamics would apply. Second, some critics say that the formation of stars and galaxies violates the law of entropy, which suggests systems change to become less organized over time. But if you view the early universe as completely homogeneous and isotropic, then the current universe shows signs of obeying the law of entropy. Third, some astrophysicists and cosmologists argue that scientists have misinterpreted evidence like the redshift of celestial bodies and the cosmic microwave background radiation. Some cite the absence of exotic cosmic bodies that should have been the product of the Big Bang, according to the theory. Fourth, the early inflationary period of the Big Bang appears to violate the rule that nothing can travel faster than the speed of light. Proponents have a few different responses to this criticism. One is that at the start of the Big Bang, the theory of relativity didn't apply, so there was no issue with traveling faster than the speed of light. Another related response is that space itself can expand faster than the speed of light, as space falls outside the domain of the theory of gravity. There are several alternative models that attempt to explain the development of the universe, though none of them have as wide an acceptance as the Big Bang theory. For instance, the steady-state theory suggests that the universe always looks the same and continues to look the same way forever.